ಏಲಕ್ಕಿ ಇಟ್ಕೊಂಡಿದ್ದೆ. Hello everyone. So today I am going to discuss about the same sequential circuits as I discussed in the previous session, the difference between sequential circuit, combinational circuits, and the examples of sequential circuits, flip-flops, and how to design this flip-flops, their truth table, excitation table, characteristic equation. All those things we have already done in the previous session. Today we are going to analyze what would be the output when I connect more flip-flops. What would be the next state? Let us analyze taking an example. Then we will discuss today how to implement the same flip-flops using Verilog code. Then we will discuss a new concept that is called as register, which is also a sequential circuit. So what exactly is the register, the operation of registers and its benefits, and we will analyze different types of registers. So how to do analysis of a sequential circuit? So as you know, we have a logic schematic representation of a sequential circuit. So from that sequential circuit, I am going to write logic circuit, I am going to derive an excitation equation. So from that I am going to derive next state and output equations. Then I am going to generate next state and output table. Then generate state diagram and develop timing graph. These are the steps involved in analysis of sequential circuit. You can just see here, first I will derive an excitation equation. How do I derive excitation equation? So yeah, we have discussed in the previous class. To derive an excitation equation, I start from truth table, characteristic table, then excitation table. From the excitation table, we are going to reduce through K-map excitation equation. So from that equation, I am going to derive next state and output equations, then generate the next state and output table. Finally, I am going to write the state diagram for the same table, then the develop timing diagram for the same. So I will take up an example to do this analysis. So this is a circuit. You can just see this circuit, sequential logic circuit. Why do we call this as sequential logic circuit? Since we have flip-flops here as a memory element, and also it contains logic gates as combinational circuit elements. So here we have a combinations of sequential as well as a combinational element here. So let us do the analysis for this circuit, which helps to explain how this circuit behaves, how it performance, how it will the performance of this circuit. So let us derive the equation for this. Let us develop a table for this. I will take up this example. We will start doing analysis. I will be drawing the same circuit here. So this is a first flip-flop. Output is considered as A, and this is A complement, and then I have a second flip-flop with output complement. So then I am applying a clock here, which is a negative transition. A bubble represents negative transition, and similarly here the clock is applied. So let us analyze this circuit. I am going to draw this circuit. The same circuit I am drawing. So clock is connected here at the both flip-flops. We have two flip-flops here, SA, RA, SB, RB. A and A complement is first flip-flop output, B and B complement is second flip-flop output. So this flip-flop connection is like this. So we have an AND gate here, which is connecting to the second flip-flop. The input to the AND gate is once again connected back to output of complemented output of the second flip-flop. Once again below AND gate is connected to second flip-flop R input, and in turn it is connected from the first flip-flop, and other end of this AND gate is once again connected to the another AND gate. So here the input of AND gate is A, and the other input of this AND gate is this. So we are connecting here. So this is the circuit. Here one more AND gate, 3 logic gates we have, combinational, and 2 flip-flops sequential. So this is how it is connected. After seeing this circuit, so this is my output. So this is a circuit where it consists of 2 flip-flops, and I am going to apply clock for this. Along with that we have some logic to produce the output from each flip-flop, and in turn it is connected to the next flip-flop. Final output is generated from the gate, the third AND gate, where it is representing X, where X is the output over here for the entire sequential circuit. So let us now, before I start analysis, since I am using SR flip-flop here, I need to consider SR characteristic equation. So SR characteristic equation already we have generated in the previous session. So in the SR characteristic equation we get next state output in terms of the input and the present output. So this represents, S and R represents input, present output, next output. So this equation is giving you the expression which is a function of Qn and input, present output and input. So the next output is a function of present output and input. So this is called as characteristic equation. We derived in the previous session by marking a table containing S, R, Qn and next state Qn plus 1. So considering this, now let us analyze the sequential circuit. So we will write a relation now for this. So what is, this is first flip-flop, this is second flip-flop. For the first flip-flop, my output is, next state output is, I am going to put this in equation 1. So I am going to substitute in this equation 1 the output of first flip-flop. So that is nothing but I am replacing Q by A, next state, then I have SA, then RA, then it is AN. So as I have given the name here, SA, RA as the input, output as AN and AN complement. So I have generated this equation. So in this equation, I can substitute SA as, you can just see here, SA is nothing but AN. SA is nothing but AN complement, which is connected in this flip-flop. So I am going to write, substitute SA is equal to AN complement, since it is connected in the circuit. Then similarly RA is nothing but your AN connection here. RA is nothing but, so AN complement. So from the circuit I am substituting this equation. So this is finally I can reduce as this gets cancels, AN and AN complement is equal to 0. So finally my expression is this. For the first flip-flop the next state is equal to the complement of the present output. So similarly, I write the equation for the second flip-flop output. The second flip-flop next state is B n plus 1. So same, reducing the expression. Now I am going to substitute SB. So what is SB? It is nothing but a combination of this circuit. So this circuit has AND gate as this connection, AN and then BN complement. So this is the input of your second flip-flop SB. So I substitute here, then RB is nothing but, once again there is an AND gate connection, AN and then BN. So this is how it is connected. I am going to reduce this equation using duality theorem. I reduce this, separate this, I remove this complement, then finally I will get this equation. In this equation, Bn complement and Bm becomes 0. So I will be left with An, this is nothing but XOR Bn. So my equation for output of second flip-flop, next state of second flip-flop is equal to A XOR B. Output of An is nothing but the present output of first flip-flop XORed with the present output of the second flip-flop. So this is what the derivation. So finally, what is X? So X is nothing but An into Bn. So X is nothing but An and Bn. This is An, this is Bn, going to get X. So finally, now after I get this equation, you can just see the equations derived here. The output from the circuit is given by X is equal to An, this is nothing but present, Xn is equal to An and Bn. If the present states, I consider present state A and Bn is equal to 0, both are 0, then, so what is the output? My output will be 0 into 0, that is 0. So then the present output is, present state zeros, then my present output is 0 into 0, it is 0. At the end of the first clock cycle, we get the next state. So An plus 1. So what is An plus 1 according to my equation? It is An complement. So what is An complement? 0 complement, that is 1. This I am going to get after next clock cycle, since it is next state. So this is present state, where note that n represents present state, n plus 1 represents next state. So when I am going to achieve this, this next state is going to appear only after the first clock pulse. Similarly, output of second flip-flop next state is equal to, according to this equation, I have got An exclusive or Bn. So where An is 0, XOR Bn is 0, 0 XOR is 0. So this is what we are going to get. So now let us analyze. After I do, this is the first step, I have generated a characteristic equation of SR flip-flop. Then from the SR flip-flop, I have generated the equation for next state. then I am analyzing now for present state, present input, and next state, and what should be my output. So now let us discuss the table that I am going to generate from this equation. So from this equation, now I am going to write a table which represents present state. I will write this as PS, then present input, then next state I will write this as NS, and present output. So how do I write the equation for this table? So I am going to write the present state is represented as we know, AN, BN, BN and AN. The present inputs, we have derived this the next state is Bn plus 1, which is nothing but A XOR B, AN XOR Bn, then An plus 1, I got this equation as An complement, my output is nothing but, so this is what I need to write. This table is nothing but state analysis table, we call it as state analysis. So as we know, we have considered A and B, there are two flip-flops, so we are going to consider this is A and B. So AN and BN represents the first flip-flop output and second flip-flop output. Since we have got two inputs, two variables, I am going to write 4 combinations. So I am going to write now 4 combinations for this. So for this combination, now I am going to generate according to this equation AN into BN of BN complement. So what is AN is 0, BN complement is 1, 1 into 0 it is 0. Similarly, Bn complement now it is 0, it has become 1, 1 into 1 it is 1, so it is 1, the rest all it is 0. Similarly, it continues. I will fill this table according to this, I will observe this inputs and then accordingly I complement Bn, and then this is nothing but AND of An Bn complement. Then similarly I fill this table An into Bn, this is nothing but 0 into 0, 0 into 1, 0, 0, 1. So what is this table? It is SA, it is input. Input is nothing but the complemented of first output. So this is nothing but AN. I have to reverse this complement 0, 1, 0. So it is nothing but as it is I should write for this 0, 1, 0, 1. So I follow this equation by looking into this 4 combinations to fill this table. So finally, this next state of second flip-flop is AN XOR Bn, we derived from the characteristic equation. So AN XOR. So I am going to take always, here we are considering the first column for doing analysis of the next columns. So AN exclusive OR of Bn. So I will fill this table. So it is nothing but 0, 1, 1, 0. As we know, XOR gate, when both the inputs are same, my output is 0, else it is 1. So this AN plus 1 is nothing but the next state of first flip-flop. It is nothing but the complemented, we derived from the equation. So we will get the complement of AN. I am going to just reverse this. So finally, I am going to write the output X. which is nothing but x is equal to an into bn. So an into bn, so first 0 0 0 0 1, this is my table. So this is nothing but state analysis table. This once again it repeats, once again the same thing repeats. I think you are clear with this state analysis table, how to draw this table. Consider present state, present input, next state, then present output. So I am going to fill this according to the equations generated. I am going to fill this table. From this table, now the next step is writing transition diagram. So let us write state transition diagram. So what is this state transition diagram? What do you mean by state? State is nothing but a task or a function that is going to change with respect to some input conditions. So changing from one state to next state, one condition to other condition is nothing but state transition. So since we have 4 combinations here, so the first state is 0 0 0 1 1 0 1 1. So we have 4 states here. I am going to represent these 4 states in terms of state transition diagram. So how to write this diagram? So how many states we have? 4 states. Since we have 4 combinations of an and bn, I will write now. So when my state, present state is 0 0, what is my output? So I am going to write my output as 0. Now I am going to write this state diagram looking into the first column and the last column. The state transition diagram give you or depicts the present state and what is the present state output, what is the expected next state. To show the transition of expected next state, I am going to write an arrow here. This arrow represents I am jumping from the current state, that is 0 0 to the next state. So what should be my next state here? According to this, it should be 0 1. So my next state is 0 1, and for 0 1, what is my present output? Once again it is 0. Note that this 2 represents present state, this represents present output, arrow represents jumping from first state to second state. So once again from this state I am jumping to 1 0 with my output as 0, and back to the last state 1 1, my output, present output is 1. This repeats. So 0 0 0 1 1 0 1 1, back 0 0. So this cycle continues. This diagram represents changing from one state to next state is called as state diagram, transition diagram. Why we call it as transition? So it is moving from one state to the other state. So it has been changed from 0 0 to 0 1, and my present, based on that I can just watch what is the present output. So this picture will give you the entire scenario of this table. So this table is called as state analysis table, and this is state transition diagram. This is how we analyze the circuit, sequential circuit, which consists of the sequential element as well some combinational elements connected. So we will analyze following this steps. So look into the timing diagram. We will discuss the timing diagram of the same circuit. You can just see here a clock is connected. Since in my circuit I have used a negative clock, bubble has been given. So this circuit responds with respect to the negative edge. So we have already discussed in the previous class what is negative edge and what is positive edge. Now this entire circuit is going to respond with respect to negative edge. So we have A and B according to my table. We have A and B, and we have generated the equations for this SB, RB, the first flip-flop and the second flip-flop output what we have got. So we have generated from the equation. So now let us analyze when this will work. Say A is equal to 0, B is equal to 0 as I derived in the equation. When both are zeros, what is my output? So 0 and it will be A complement, it will be 1. It is of course a 0 here. So SB is 0, RB is A and B, it is once again 0. What is SA? It is A complement is 0, we have got 1. What is RA? RA is nothing but A. This we got it from the equation. So what is the output? When you will get this output, output is nothing but X is equal to A into B. When you are going to get this output, so this is with respect to the first clock pulse your inputs are given. When you get the next pulse here, you are going to get output. So you can just see after this first transition, the next state is responding. After this, you can see your output X is equal to A into B. So X is equal to A into B, as we have generated, it is 0, so we got the output here. So once again, if I change this A and B as 0 and 1, this reflection is done in next coming clock pulse. So this is the timing diagram of the sequential circuit. Now let us discuss what we have already discussed about a latch, flip-flop, different types of latches and flip-flop, D flip-flop, D latch, SR flip-flop, SR latch. So we have already analyzed and discussed the difference between latch and a flip-flop. So now we are going to discuss how to write a Verilog code for this latch. So we have considered here two examples here. You can just see here a latch. Always a Verilog code starts from the keyword module, and this is your file name. So module name. So in the module name, so there is a port list inside this. Port list represents inputs and outputs. So here the input I have considered as D. Since it is a D flip-flop, has got a single input and single output, and since it is a latch, there is a difference between latch and a flip-flop. Note that since I am writing this for latch, I should use enable signal. If I am using as a clock, then it is a flip-flop. So the signal is enable, so it is a latch. So I am giving enable as a signal. So output is Q, your input is D and enable. So I am going to store this output once again as a temporary variable in reg. I mentioned this as a reg Q. Here I am using a conditional statement always at enable or D. So this condition executes only with respect to these two signal. Whenever any of this signal changes, if enable so is high, then Q follows D. So this is a simple latch. When you are going to enable, then Q follows D. So similarly, SR latch, we have SR, two inputs, one output. I am considering an enable signal here. You can also consider complemented output also. Still you can add this. Output is Q, inputs are S, R and enable, and we have a temporary variable that is reg Q. So always at, once again the conditional statement over here. So either of enable or of S or of R, any of these three signals going to change, then condition if enable is there. So we have derived a characteristic equation as I discussed in the previous, Q is equal to S or R complement into Q. So this equation we have generated, this equation is nothing but characteristic equation. So I am going to get the next state, that is next output. So output is a function of your present inputs as well as present output. So this Q represents the output with respect to the function S and R. This equation is nothing but a characteristic equation that we have generated in the previous sessions. Now I am going to consider here one more example, same SR latch, except I am not using any enable here. I am just giving here the terminology, port list as Q bar represents, that is Q complement, S complement, this is S bar R bar, S complement R complement latch. I am going to write a Verilog code for this. So, I am giving this as an inputs, and Q bar represents output. So, this is the declaration given here. So, as you see in this latch is made up of NAND gates. We have two NAND gates here, N1 and N2, and output of the NAND gate is connected as an input of the other NAND gate. Crisscross connection is here. So, now I declare this NAND gate as N1 and N2, it should be N2 here. So, NAND N1, this Q, the inputs are S bar and this is Q bar. This port list gives the output and followed by inputs. So, NAND is a keyword. So, whenever I use this keyword, automatically the latch is created using NAND gate. If I give NOR here, so the latch is built using NOR gate. So, similarly this is N2 here. So, N2 we have Q bar as an output, R bar as an input, plus we have the crisscross connection, that is feedback connection of the first NAND gate output, that is Q. So, this is another way of representing SR latch. This is a Verilog code for SR latch in the other method. So, now I am writing for SR flip-flop. As we know, there is a difference between latch and a flip-flop. Latch is nothing but it is triggered by enable signal. Flip-flop is triggered by a clock signal. A clock can be either positive edge or negative edge. Enable can be either positive level sensitive or negative level sensitive. So, now I have written a code here for SR flip-flop. You can just see here, I have named this as flip-flop module as part 1, clock output, inputs are R and S and Q. So, input is clock here, there it was enable. So, I am using a wire here. So, what is this wire? So, it is nothing but intermediate connections where this circuit is made up of additional 2 AND gates, as we have discussed in the previous class. I will take an diagram for this and I will explain. So, clocked SR is nothing but your SR flip-flop is used with NAND gate, is built with NAND gate, and we have outputs here, and this is connected by a clock, and this is S and R. So, this is nothing but clocked SR flip-flop. So, I am considering this as S underscore G, I am considering this as R underscore G, this output, these are intermediate output. So, we have 2 AND gates and we have 2 NOR gates. So, now I am going to write code for this. So, I need to consider this gate separate, this gate separately, and this gate and this gate. So, this is how it is written in the code. So, in the code you can just see here wire, these are intermediate outputs R underscore G, S underscore G, these are coming from AND gates, and then QA, QB. So, AND gate, these are AND gate output, input, clock, AND gate, second gate, once again S, this is the output, intermediate output, input and clock, and NOR gate consists of output, the first output and the inputs from the AND gate. Similarly, finally I assign Q is equal to QA. So, this is my final output. The other method of writing same SR flip-flop is by considering your case statements. Since we have 4 combinations, 2 inputs, 4 combinations, I can write using case statement. So, we have your outputs, inputs and clock. So, output is represented as Q and Q1. So, you can represent either it as Q complement or Q bar, anything you want, any variable you can assign. So input R, S and clock, and we are considering reg here. Begin, Q is always this 1 represents 1 bit, tick B represents binary. So I am representing the number in binary with 1 bit. So that is nothing but 1 tick B. Suppose I am representing 3 bits, I should write 3 tick B 0 0 0. So this is how I am going to write. So initially I am assigning my output here as 0 and complement will be 1. So initial condition assuming here begin and end. So this declaration is nothing but I am assuming the outputs as 0 and 1. Now at respect to positive edge of clock. So when the clock arrives, so what exactly I should do? Begin with the K statement, S and R inputs. I take two combinations 0 0 0 1 1 0. If both are 0, so as we know the truth table of SR flip-flop, there is a no change condition. No change, whatever the previous, the same thing is stored here. So when it is 0 and 1, the output is in reset condition. So that's why 0 and 1. My output is 0, 1 here. Q complement. So if I give 1 and 0, it is in set condition. My output is 1 and the complement is 0. 1 1 condition, since it is forbidden condition in SR flip-flop, so I write this as X, which is not considered as any state. So end, I should start with begin and end for each statements, because each statement has got different cases. I should begin and end for each case here. So end case statement, the case statement is closed by the statement end case and begin is closed by end. So finally the entire module is closed by declaring end module. So this is the HDL implementation of SR flip-flop. So similarly I can write for D flip-flop. As you know, D has got 1 input, 1 output, clock. Additional input I am going to give here as clear. So what is this input clear? Clear is nothing but whenever I want, I can reset my flip-flop. I can reset this D flip-flop by making clear 0. No matter whatever may be the input, if my clear is 0, the flip-flop gets reset, cleared. It is cleared is nothing but it only stores 0. So I am going to give here the variable output as Q, input D, clock and clear, and reg of course a temporary variable where I am storing this output. So now the condition always at. So either at the positive edge or if the negative clear comes, then my output if tick clear, so not clear means if clear is 0, my output is 0, else Q follows D. So if my clear is I, so whatever the D input I am going to give, that is passed to the output. Suppose I have given the input, still my clear is low, then definitely your input is not sent to the output. So your flip-flops are cleared here. So that is the meaning of another input called clear input. So where we call this as an asynchronous input, other than your clock is a synchronous input, clear is an asynchronous input. So similarly there are different variations. I can write the D flip-flop. You can see here. Here I am using only clock. With respect to clock, Q should follow D. Here I am using negative edge clock. Here I am using positive edge clock. So there is no as such difference here. Only the clock where I am giving positive, your output should respond. The D flip-flop should respond either with respect to the positive edge or with respect to the negative edge. So separate modules have been created for this. Similarly, we have JK flip-flop here. So in the JK flip-flop, as you know, 2 inputs J and K and outputs, normal output and complemented, and we have clock there. Similarly, I declare and also I declare the previous as assume that my output is currently it is 0, complement is 1. So always with respect to positive at C, here C represents clock, either I can give C, CLK, CP. So terminology or a variable depends. So begin, once again I am using a K statement for all this J and K inputs. Since we have 2 inputs, we are going to generate 4 different combinations here. So for each of the combinations, I am going to write begin and starting with the statement begin, and I am going to end this. So we can see this 4 combinations. begin and then end. So 0 0, as you know, no change condition in JK flip-flop. 0 1, it is once again reset condition. 1 0, it is set condition. My output is 1 in case of set condition, my output is 0 in case of reset condition. So 1 1 conditions, it toggles. Toggle in the sense I am using here a NOT operator. Q becomes Q complement, Q1 becomes Q1 complement. So whatever the stored previous Q will be complemented, that is called as toggling. So I use an operator for toggling as NOT operator. So I end this with end case and then begin is closed with end statement. As usual, a module is closed with end module. So now let us discuss the concept called as a register. So what is a register? Till now we have discussed flip-flop. Now I am discussing a register. A flip-flop stores a single bit, that is either 1 or 0. Suppose I need to store multiple information. So binary information, which is a 4 bit, 8 bit, 10 bit, like that. As such, how many flip-flops do you require? Suppose I want to store 3 bit data, then how many flip-flops do you require? Yes, we require 3 flip-flops. So each flip-flop has a capacity to store a single bit. Multiple bits, I need to consider more flip-flops. So for that, an array of flip-flops or a group of flip-flop is termed as a register, which stores the information. It is a memory. Once again, it's a memory. The register, what is the function of this register? The register is used. So function of a register is to store data. Where it is used? Suppose I represent or I accept input data from a keyboard, and then I should present it on this data to the processor. Then this has to be sent through the memory itself. So I type on the keyboard, I press the data from the keyboard. So this data has to be passed to the processor. How it is passed, how it is stored? This binary information is stored in a temporary register. From that register, it is sent to the processor. This is how the information is passed through this register. Suppose I want to perform arithmetic operations like multiplication, division. So how it is done? Once again, it is done using through registers. Suppose I want to count number of pulses. So entering into the system. So for example, up counter, down counter. So in the coming modules, we will be discussing about the counters. So before that, we use this registers in counter applications. And for serial addition, sequence generation, sequence detecting, for all these applications, we need to store data, an array of data. To store that, I require an array of flip-flops, that is nothing but a register. So benefits of this register. Since the limitation of flip-flop is only 1 bit, so I will be using more of flip-flops to store more of data. Most of the computers operates on integer and single precision floating numbers. For that, your data will be more, 32-bit long, 16-bit, 32-bit processor will consume the data at a stretch 32-bit, 16-bit. That time I need a storage element to store at a stretch this 32-bit long data or a 16-bit long data. Then I will be using a register, an array of flip-flop to hold this data. So register is once again an extension of flip-flop which is storing multiple bits. It's commonly used as a temporary storage in the processor. It is more faster than the main memory. Instead of fetching the data from the main memory, instead I can fetch the temporary data. I can store this temporary data in the register, and the time consumption is less compared to fetching the data from main memory. So most of the register as used can help in speed up the complex calculations. So basic register, how we are going to build? I will take up an example of 4-bit register. Usually the register is built of D flip-flop. We use a D flip-flop to build a register. Why D? So D flip-flop does nothing, it just transfers the data. That is what is required for our register operation. We need to store my data, I need to send my data, store data. That's why I am going to use D flip-flop. So without worrying about the equations, I am just using D flip-flop to store the to build a register. So if I am using if I want 4-bit register, then I will be using 4 D flip-flops. So we just see this diagram. In this diagram, you can just watch how many flip-flops I have used. 4 flip-flops. Each flip-flop has got an input which is named as D0. This represents LSB. D1, D2, D3. D3 represents MSB. So I am going to connect this Q. I am taking this output directly from here. I am doing nothing. I am giving 4 bits input to each of the flip-flop, and I am taking 4 outputs from each of the flip-flop. So all this, when this flip-flop should respond with respect to clock. So whenever a clock appears, you can just note down here, the clock is connected simultaneously to all the flip-flops. Why? Why? Because if I apply a clock to a single flip-flop, only you can get the output here as a single instant. I want my output as a 4-bit. All 4 bits should appear simultaneously. It is not single bit. So that's why when all these 4 should come out with respect to some means, some control. So which is that control signal? Clock. So that's why whenever the clock appears, immediately for all the flip-flops, you can get the output. So in turn, I can make all this flip-flop 0 or reset by making an additional input called clear. So whenever the clear is 0, you can just see here it is a active low input. So when 0 appears here, all your flip-flops are cleared. So this is a basic register build 4-bit using 4D flip-flops. We will discuss type of registers here. So registers is nothing but once again group of flip-flops. This register can do 2 operations. Either I can do serial shifting, I can do parallel shifting. So I can send my data through this register one by one, 1 bit after the other bit. This is called as serial shifting. So 1 bits are shifted to another. For each clock pulse, 1 bit will be shifted. Parallel shifting, when I apply clock, all the 4 bits are shifted simultaneously. So during the clock transition, all 4 bits appear parallelly. That is called as parallel shifting. So based on this, we are going to define the types of registers here. Serial in, serial out. So we have the corresponding ICs available, 7491 for 8 bits operation, serial in, parallel out, then parallel in, serial out, then parallel in, parallel out. So we can just consider all this ICs available are of 8 bits. So shifting operations you can just see now using the shift registers. In the previous diagram I just show the basic register. Now I am showing the shift register, shifting operation. All the clocks are connected to all the flip-flops and I am giving an input here. It is called as serial input. I am giving from here. So first flip-flop, for first clock pulse, the first bit comes over here. Other flip-flops will be holding the previous data. The next clock pulse, this bit is shifted to second. In the next clock pulse, the second is shifted to third, and the next clock from third to fourth. So it requires 4 clock pulses to send the data. Since we have 4 flip-flops, it requires 4 clock pulses. So you can see the example, I am sending the serial input as 1. So my output Q0, Q1, Q2, Q3, 0, 1, 1, 0. Suppose it is holding 0, 1, 1, 0 in the previous state. So when I apply SI is equal to 1, this last bit, that is 0, is lost, and this 1 and 1 appears here, and the serial input I am giving as 1. So I will get 1, 0, 1, 1. So this is how this SI, the color represents 1, is a serial input what I have sent. Blue represents which already previously present, that is been shifted right. So the last bit will be, that last 0 will be lost on the next clock cycle. This is how the bits can be shifted. So I will take up first example, serial in, serial out. We have serial in input, serially we are taking the outputs here. So the bits, as I discussed in the previous diagram, I am shifting the bits serially. You can see the output here. So Q0 represents the first output, the data what I am giving as 1. The next clock pulse, this 1 is shifted to the next register. Next clock pulse shifted to the third register output. Fourth clock pulse, you will get the output here. So this is how the bits are shifted right. Either I can make it shift right operation, or I can make it shift left operation. For shift right operation, I have started from this side. For shift left operation, I'll be giving input from this way. So this is how I can do either right shifting or left shifting. So serial in, serial out transfers takes place depending on number of bits you are using. If I am using 4-bit register, it takes 4 clock pulses to shift the datas. So it is shifting from first flip-flop to second, second to third, third to fourth. That is how it is transferred to the till last. So the same thing has been discussed in the timing diagram. You can just see here, data in is 1011. I need to imagine that there is this square box represents a register which is clear, nothing is there. Now I am started sending 1011. So the first bit will move here, then clock pulse is applied. When the clock pulse is applied, the next bit is 1. The next bit, this 1 will shift to the second flip-flop. The next bit 1 will come here. Next clock pulse is applied. This 1 is shifted here. This 1 is shifted in this, and the 0 will appear here. Next clock pulse 1 is shifted here. Then this one 0 and 1. The next clock pulse. So now all flip-flops have been filled with 1011. Still, if we gave the next clock pulse, the last bit will be lost. So you will be remaining with 101 inside the register. This is how the shifting serial in and serial out I can take up the data. So today session we have analyzed a sequential circuit, how to draw an state analysis table and how to write a state diagram. Then we have implemented many flip-flops and latches using Verilog code. Then we have discussed what is a register, benefit of register, types of register. The next coming session we will go in depth of all 4 types of register with a circuit diagram and the timing diagram. So we will be discussing in coming session still more about the register operation. Thank you.